Hey, Algebra 2, coming at you with some transformation notes. So this is a pretty cool unit. So it's quick and fun, but I want to talk to you about these notes. I can transform parent functions. So what's cool is I want you to think about any of these parent functions as our good old f of x. And we're going to move these things all around the coordinate plane. All right. So we're going to look at each of these functions, and I want you to think about how the red dotted graph. So I'm going to take my red pen and make sure you know that this is my parent function. So that's a quadratic. And then this is my parent function. This is a cube root function. That's kind of crazy. And then here is another parent function, and we're going to learn about this guy. He's an absolute value function. And then we're going to talk about this guy here. Here's my original, and this is going to be my square root function. So we have each of those parent functions, and what I want you to consider is something's been done to them to change them. This one ended up kind of blowing up, going taller than he's supposed to be. This one ended up like flipping over the axis. And he's looking a little wider too, if you ask me. This one looks the same exact. It just looks like somebody gave him a boost up in the air. And then this one's kind of interesting. Somebody pushed him back and down at the same time. So we kind of ended up moving almost in this diagonal sense. So we're going to talk about each of the things that make that happen for each of these graphs. We can move the functions around the coordinate planes by making changes to their equations. And these changes we make to the equations follow some pretty great rules. If we start with the equations, our original function, remember we have f of x to start with, we can adjust its position on the coordinate plane. Now check it out. When I add a constant, it's going to move my graph up. So when I stick a constant on the end, my whole graph is going to shift up. When I subtract that constant, my graph is going to move down. Okay, that totally makes sense to me. So when I come back to this one, I wonder if this just had a constant because it pushed it up. I wonder if that's what happened. All right, our next conversation looks like we're moving left-right. But notice this value is inside of the parentheses. If it's subtracting, it's going to go right. That's the opposite of what I would think. Because here, when I was subtracted, I moved in the positive direction. Here my subtraction, or here addition moved in the positive direction. So when I go left, that's my positive. That's kind of crazy. All right. When you have a negative outside in front of it, that's going to flip it. So that's going to reflect it over my x-axis. So we're going to take that whole graph and we'll flip it. That feels like this one. Doesn't it feel like this one was flipped over that axis? Okay, so when I have an a out front, when I have a coefficient out front and the absolute value of the a is bigger than 1, then that means my graph is going to stretch. It's going to go tall and skinny. So it's going to be taller graph and it's going to be skinny. It's going to make those output values much higher, faster. If my a out front, notice it's between 0 and 1s, which means it's going to be like a fraction, right? If I have like 1/2, 1/3, 1/5, then my graph is going to be compressed. It's going to be fat. It's going to be a fat and wide graph. It's kind of what I feel like is happening again with this one. See how he looks more spread out? I wonder if that's that one. Okay, so here's it, the same conversation but in different words. So we can look at where our h and k and a values are in our equation. If an h value is inside of the parentheses like that, it's going to shift the graph left-right. If a K is outside of the graph, like this, it's going to shift it up, down. If an A, that coefficient, and I want you to think about slope now. We're not all linear, but it's going to do the same thing, steeper slope, and then that compression, that lower, flatter slope. And then again, if we have a negative, that's what's going to give us a reflection over the x-axis. Okay, so let's take a look at page 2. Given this parent graph of f of x, here it is, and we can practice these transformations. And if you can print this out, awesome. If not, you should draw it on a coordinate plane so you can practice doing this. All right, so if I have an f of x plus 1, if I look back at my rules, that looks like I'm going to have a k outside, which means I'm going to go vertically up. So this transformation is going to go up 1, which means each of these dots on my graph is going to go up 1. So my transformation up 1 looks like I have sent my whole graph, just given it a little boost up in the air. All right, let's try another one. This time I have a negative out here, but then I have a positive in here. So let's go back and look at what happens when that number is inside of the parenthesis. When it's inside of the parenthesis, it's going to shift left, right, and it's opposite of sign. So let's see, it's plus, which means it's going to go backwards. So this graph is going to go to the left 1, and this negative is true to sign, and it's going to go down 2. So let's see what that does. Now remember, we're going to go from our original. So we're going to go left 1, down 2. That's its new dot. Left 1, down 2. Oh, I got my words in the way. Left 1, down 2. And left 1, down 2. So now this graph has two things going on. It's going to be shifted to the left and right, so you get that diagonal pull. That's kind of cool. All right, this one's kind of fun. Our transformation is just one thing going on. It's going to be a reflection. So every single point I have is going to go opposite. Now here's the thing, if I'm on the axis, I stay on the axis. This point here is 1, 2, 3 away. So we'll go 1, 2, 3 away. All right, and this point is 1, 2, 3 away. 1, 2, 3 away. And this point is 1, 2, 3 away. 1, 2, 3 away. So do you see this pink straight line is going to be the flip of this graph. So that pink is going to be that flip. I think we're going to get a little bit of a messy graph here, but that's okay. Now I have another flip, so I have a reflection, and I'm going to go, this is -2, which means I'm going to go to the right 2. And the question is here, what do you do first? And you're going to dive in to our order of operations. So I'm going to take my graph to the right 2, and then I'm going to reflect it. So this is going to go to the right 2, right, and then reflect it. So 1, 2, 3, 1, 2, 3. So here's that part there. And then this part is going to go to the right 2, 1, 2, and it's going to go 1, 2, 3, 1, 2, 3. And this last point to the right 2, 1, 2, and I don't need to reflect. because it's on the axis. So what's interesting is we can see the relationship between the pink and the green. They're both reflections, but shifted over. All right, let's talk about this. We have a lot of reflections here. Here's another reflection, and then down one. So we're going to reflect, and then we're going to go down one. And then for this graph, we're going to stretch by 2. Okay. So you ready for my reflect and down 1? All right. Reflect down 1. I'm going to highlight my original graph. I'm kind of losing it here. That's my original graph. All right. So I'm going to reflect 1, 2, 3, 1, 2, 3, down 1. So that's my first drawing. All right, this point here, I'm going to reflect and then come down 1. So this is going to come all the way down here. And then reflect, 1, 2, 3, down 1. So here's the rest of that graph. Hey, the stretch by 2 is kind of cool. So each point you multiply by 2. So see how this one is rise by 3? Your output is going to be multiplied by 2. So 3 times 2 is 6. Actually, I already used purple or red. So we'll go ahead and use. This is multiplied by 2. So it's going to be 6. It's super tall. Now, this point here, 1, 2, 3 is also going to be multiplied by 6. Or by 2 to get 6. So 3, 4, 5, 6 is going to be here. So this whole graph, whoop, is going to then look like that. Wow, what a mess. Okay, for each function, write the equation of the solid line graph. The parent function is that. Okay, so here's our parent function, and we'll go ahead and we'll highlight that. What happened to g of x? If I have g of x, that's this dotted function, and what does it look like happened? It looks like we just pushed it up 2. All right, let's talk about h of x. What does it look like happened to this guy? So here's my original, and it looks like 1, 2, 3, 4 is the shift. So we are going to do minus 4, get rid of that. Because, oh, wait, no, it shifted to the left, which means it's got to be positive. Nice. And then it looks like we went down 2. So 1, 2, 3, 4, down 2. So h of x plus 4 down 2. All right, let's take a look at our parent function. What do you think happened here? It looks like it's definitely a reflection. So we've got j of x. And it looks like we shifted 1. Well, let's do this first. 1, 2, 3 in this direction, so plus 3, and we reflected. And then how far up did we go? 1, 2, 3, and then we reflected, and then we went up 2. How'd you do? Now there's a great Desmos activity that I want you to do, and that's going to help you. But let's go back to those 4 graphs that we talked about originally. If I have f of x as my dotted line, 1, 2, it went to the left, and then it went down 3. Let's see about g of x. G of x is my cube root function, and it went up 1, 2. Let's talk about my absolute value function. N of x, it looks like it reflected. It looks like it's about a 1/2. Let's see, rise 1, 2, 3, 4. Uh-oh, it's a 4th. And it went back 1, 2, 3, 4. So we'll do, and it didn't go up or down. And this S of x looks like it's been stretched up. And when we look at this point here, it's double, so we'll say 2. Nice. All right, so a real quick conversation about linear equations. You're used to seeing them as y equals mx plus b, slope-intercept form. But when we put it into the point-slope form, we can see these transformations. There's 2 versions of our transformation. One where we have our y minus y1, and the other where we add that y1 to each side, and that's what gives us this guy here. A is like the slope of the line, and HK is like a point on the line. So when we have our transformation, we can go ahead and say that our y is equal to our A. So instead of the slope, we'll write the A. And that'll be times x minus h. That h is like my x coordinate. And then plus k. So you're going to be seeing this a lot. It's the template, the format, the basis for how we move all kinds of equations around the coordinate plane. So we can look at this equation and see, oh, wait a minute, look at that. That is a stretch of 2. We can look at this and say that that needs to go to the right 3. And we can look at this and say, oh, that's going to make it go up 4. So we have our transformations, a stretch of 2. We can say it's going to the right 3. And we can say it's going up 4. Let's check out this guy. Now we're going to have to get rid of this 2, put it back into the format, x plus 1 minus 2. Subtract 2 from each side. Now here's the deal. We don't want to combine like terms or else I can't see the transformations. That's our goal here. So I know that this means that my graph is going to the left 1, and that this means that my graph is going down 2. Alrighty, here we have, check it out. We have a reflection. We have a stretch. We have movement to the left, 5. And we have movement down 1. All right, you ready to pick apart this one? First, let's take care of this too. Y is equal to 1/3 times x minus 5 minus 2. All right, let's talk about all the individual pieces. This, my friends, is going to compress the graph and make it flatter. This is going to move it 5 to the right. And this, say it with me now, is going to move it down 2. Okay. Write the equation of the line in point slope form containing this point with a slope of 2. Are you ready? Point slope form is the easy one where all you got to do is fill in the boxes. So it's y minus y1 slope times x minus x1. Ready? containing that point and that slope. So we have y minus, what's your y? 3 is equal to your slope, 1/2 times x minus -1. Nice. Write the equation line containing this point is parallel to this. Parallel lines, remember from algebra, have the same slope. So that's all I need to steal from this guy is his slope. So y minus -5 is equal to my new slope, parallel, times x minus that x value. Bingo. Alright. And my next one, write the equation of the line containing that point. Perpendicular. Okay, perpendicular lines have slopes that are opposite reciprocals. So if this slope is equal to 2/3, guess what? The slope of the perpendicular line is -3/2. You remember that from geometry. Alright, so write the equation line containing this point. So y minus 2 is equal to my new slope times x minus 2. And now I need to go get it. -3/2. Alright, we're going to do lots more of these, but what a great introduction. Have a good weekend.